So far, we've concentrated our discussion of phase behavior in two-component systems to ideal solutions. And in this part of Lecture 11, we're going to talk about non-ideal solutions. But let's first talk more about ideal solutions. So far, what we said was for an ideal solution, Raoult's law is followed. So if you look at the total pressure, say as a mole fraction of component 1 going from 0 to 1, Raoult's law says that this should be a straight line and that the partial pressures of each individual component would be straight lines. So if this kind of plot of a temperature composition phase diagram, or actually just plot a total pressure versus composition, if these give straight lines, then you have an ideal solution. There are a few other consequences of having an ideal solution. For instance, the change in volume here, when the two solutions are mixed, should be 0. Now let's look at that in more detail. So let's consider our system as just be two compartments separated by a partition. This is component 1 and this is component 2. And then what you're going to do is to remove this partition so that we now have a mixture of component 1 and 2. They're all mixed out here together. The idea here is that if you have an ideal solution, the following interactions are negligible. The solute, the solvent, and the solute, interactions. These interactions are all negligible. In other words, it's as if these two components here don't see each one another and they just go about their business as if the other didn't exist. This, it may ring a bell. This is what we said about ideal gases. When you mix ideal gases, it's as if the one ideal gas doesn't see the other ideal gas. Same idea for liquid solutions. So if there are no interactions, actually negligible, actually there are none in the limit of ideal solution, that means that the volume, for example, if you have a certain 100 milliliters here and 100 milliliters here, when you move the partition, no interaction, you should end up with 100 plus 100 or 200 milliliters. So that means that the volume of mixing should be 0 if you have ideal solutions. And if you look at the work, work is P dV, or P delta V of constant pressure. That work is 0. And since there's no interaction between the solute and solvent, or solvent-solvent, or solute-solute, what that means is that there should be no heat generated and so on. So Q is equal to 0, delta U is equal to 0, and delta H is equal to 0. So all these quantities are equal to 0 for an ideal solution when you mix the two components. However, if we look at here, this is spontaneous. Our common experience shows that if you have just one beaker in which you, on one side of the beaker, you put some component, and the other side of the beaker, some other component, they will spontaneously mix so that one will diffuse through the entire solution, as will 2. So that means that if it's spontaneous, delta S cannot be 0 and delta G cannot be 0. Right? So remember our criteria for spontaneity. So at constant temperature and pressure, our criterion for spontaneity is delta G has to be less than 0. Well, if we go back up here, this looks very similar to the situation we had when we were mixing ideal gases, except now the solutes are 1 and 2. Everything is a solvent except for the solutes 1 and 2, the two different solutes that we're going to mix. So, as you might expect, you get the exact same expression for mixing of the two solutes. for delta G is just RT times this sum over all solutes of the mole fraction of the solute times the natural log of the solute. So these are mole fractions here. And you could refer back to our discussion for ideal gases to figure out where this comes from. And also the entropy, delta S of mixing, is just minus R times the sum over all solutes of the mole fraction of that solute times the natural log of the mole fraction of the solute. Again, almost exactly analogous to the ideal gas case where you're mixing two gases. Okay, so that's what happens. You have ideal mixing. You'll just have these two expressions for delta G and delta S, constant temperature and pressure here, and everything else is zero when you're mixing them because there's no interaction between anything. Now let's look at non-ideal behavior. Well, non-ideal behavior means that these things won't hold. So for example, if you mix water and ethanol, water and alcohol, you'll have a volume that is not double the water and alcohol you've mixed. In fact, to be less than that. 100 milliliters of, say, scotch and 100 milliliters of water will not give you 200 milliliters of solution. It'll give you less than that. And in fact, that's if you're a bartender, you might run into that problem because somebody says, hey, you know, I ordered 2 ounces and there's only like 1 ounce and 3/4. Work might not be equal to 0, Q, delta U, and so on. So those thermodynamic quantities are not equal to 0 if they're non-ideal behavior. And then another definition of our ideal behavior for two liquid components was that the total pressure follows Raoult's law. Raoult's law, recall, was this. So if you don't get straight lines, if you plot total pressure versus mole fraction of one of the components and it's not linear, well, what does that mean? That means it's non-ideal behavior. Okay. So the mixture does not follow Raoult's law. Let's take a look here. Here's an example of a couple deviations of Raoult's law. What we're plotting here is a total vapor pressure. That's the partial pressure of both components, P1 plus P2, as a function of composition. In this particular case, we were using 1 and 2. Component 1 goes from 0 to 100, and therefore component 2 goes from 100 to 0. Straight line, Raoult's law. You can have what's called positive deviation from Raoult's law, where the total pressure is greater than that you expect from Raoult's law. It's positive deviation. Or you can have negative deviation from Raoult's law, where the total pressure you measure above the solution for a particular composition is less than that you would expect for Raoult's law. This upper or lower curve, if you see that, then you find solutions, then you would conclude that the solutions are non-ideal. And in fact, most solutions you make by mixing two liquid components are non-ideal. Okay, and then you have what's called an azeotrope. An azeotrope is water and vapor and liquid have the same composition. Well, actually, let's just go and take a look at what we mean by that. Now, this is a temperature. Let me switch the ink color to black again. This is temperature versus composition. So this is a temperature composition. And remember, for those kinds of plots, up here, the upper region is where you have vapor only. The lower region is where you have liquid only. Whereas if you look at pressure composition plots, then these two things are switched. For pressure composition, we have pressure up here and vapor down here. And then there's a region between those two, one phase only, in which you have two phases, vapor and liquid. Now, what we looked at before, we had a dew point line. Let's switch back to white here. Oh, I guess it was already on white. We had the dew point line. So if we look at temperature and pressure composition here, we had something like this. Here we'll go from, so usually you draw an axis, a vertical axis out here at 1, and we start at 0. And then we had something that went down like this. And the region here was liquid plus vapor. And so there's all this region here. That's what it looked like for, this is not characteristic of an ideal solution, but if you have an ideal solution, you would have something like this. On the other hand, if you see something like this where there's a point here where, in fact, the two lines, the dew point line and the bubble point line, come together and meet. They don't cross one another. And that right there is an azeotrope. So at this particular composition, you'll get a mixture which there's no separation between the dew point line and the boiling point line. What does that mean practically? Well, let's say we start at this particular composition and we increase the temperature of the liquid, and finally we get to boil. We collect the vapor. We then condense the vapor into a liquid. We then boil that again, condense and boil. But what you see here is that you're never going to get a pure substance. In contrast, here, if we say it starts this composition, so we boil, condense, boil, condense, boil, condense, eventually you get over here on this axis. But for an azeotrope, you get stuck right here in one particular spot, and you can't, because they're meet, you can't go above that. Okay, so this is the, if you start over here, that's the maximum concentration you can get for component X or Y. We'll call this component 1 or component 2. So, so this would be, say, X1. All right, well, maybe if we start over here. So let's start over here. Okay, so we're going to boil, and then we're going to get the liquid, condense the liquid, boil, condense, boil, condense. So you start over the other side, you're just going to end up at the same place, the azeotrope. An example of an azeotrope, by the way, is ethanol and water. At 95% ethanol and 5% water, this forms an azeotrope. So if you start with a ethanol-water mixture and do this, try to separate out pure ethanol from that, you can only get up to 95% ethanol, because at 95% ethanol, 5% water, you form an azeotrope, and you can't purify it anymore. You're like right there. So that's why if you go into a liquor store, for example, and buy you try to get pure ethanol, what you'll get is 190 proof, which is 95% ethanol. Okay, so that's an azeotrope in which you have a lower, so the azeotrope boiling point is lower than the boiling point at either end here. This would be pure component 2, and this would be pure component 1 right here. And then the azeotrope then would boil at a lower temperature than either one of those. This kind of behavior, in which the boiling point of the azeotrope is less than that of either pure component, is called a positive azeotrope. Let's consider another azeotrope. This would be like this, and if that was called a positive azeotrope, this one is called a negative azeotrope. Okay. In this case, the boiling point of the azeotrope is greater than the boiling point of either pure component. And let's change to our notation. This would be mole fraction of component 1. So this would be the boiling point of component 2, where you have no component 1. This would be the boiling point of component 1, where you have no component 2. And the mole fraction will go from 0 to 1. All right, so let's start, say, with this composition, and we're going to heat it up. We're going to go up here to the boiling point And now we're going to boil that composition. We're going to collect the vapor over here, and we're going to condense that vapor. We're going to boil that, condense, boil, condense, boil, condense, and so on. And eventually we're going to end up out here with pure component component 2 and 0 component 1. Let's see what happens if we say start over on this side. So let's say start at this particular composition. There it is. We're going to boil it. So there's the vapor. We're going to collect that vapor, condense it to a liquid, boil, condense, and so on. So we'll end up over here, where now we have pure component 1, 100% component 1, and no component 2. The point here is that no matter where you start, you'll never go past the azeotrope. So here you always regress back to pure component 2, no component 1, or if you start on the other side of the azeotrope boiling point, you'll start here and you regress back to pure component 1 and 0 component 2.